Again, I'm Aaron Volkman, and I'm going to be talking to you today about malware distribution networks. This is a Lens project that I collaborated with Dr. Jose Morales and Dr. William Casey on. And I'd like to start off this presentation. Imagine with me your 11-year-old son or daughter at home using Google Chrome on their laptop, browsing Russian Facebook or something. And they happen to click a random link in some sort of post that they see. And they're encountered with a page that looks like this. And the site ahead contains malware. So where did this come from? This came from Google Safe Browsing, Google's service to check a URL before you visit it to see if they know that this URL is bad. You see here that this is for 9down.com, and every page the Google Safe Browsing blocks contains a diagnostic page. Here we see a Google Safe Browsing diagnostic page for overtheedgemovie.com. And what I'd like to draw your attention to is that there are a couple questions that are asked on this page that are answered. Has this site acted as an intermediary resulting in further distribution of malware? And has this site hosted malware? We see the answer to those questions are some links that indicate other sites that have been infected by this particular site. And we could click on these links and view their Google Safe Browsing diagnostic pages to see who they infected. So as part of this research, we start constructing a mathematical graph structure programmatically. We take a look at a known infected page, Google Safe Browsing diagnostic page for a particular domain, and that is a node on our graph. And then we take a look at who that site infected, and we look at their pages, and we draw an edge between those nodes in our graph structure. And then we visit each of their pages and all their children and who all they infected. And as you see, and then we continue traversing all the children, the tree structure, and our graph gets bigger and bigger and bigger until we have constructed our malware distribution network. So what does this mean for the DoD? What can we do with this data? Well, the first thing that we wanted to see if we could accomplish by collecting this kind of data from search engine data is early threat indicators. In this graph, the orange line at the top comes from our data. What it is the number of nodes in the graph that we collected. Along the x-axis is the dates, because we do this collection every day. The purple line in the middle are the number of incidents submitted to US CERT, aggregated up, and the multicolored lines at the bottom are the ticket types submitted to US CERT broken out by incident type. And what we noticed was a spike in our data starting here on January 28th and ending 4 days later. And then immediately after that, we observed a spike in the number of incidents reported to US CERT. And what we think this means is that the increase in the number of nodes in the malware distribution network indicates a buildup of a capability, and then in response to some sort of cyber event, humans were reporting incidents to US CERT as a result that you see occurring after the buildup. So this shows promising results that we could use this data as some sort of early indicator of a cyber event that's interesting to us. Another aspect that we looked at is graph robustness. How hard would it be to disrupt the spread of malware over the internet via this methodology? So what we did was we took our malware graph and we mathematically split the graph in half into two equal parts using a program called METIS from the University of Minnesota. We identify what nodes would need to be affected and taken down in order to cut the graph in half and split the graph in half every day for every data collection that we conducted. And this is a graph of the results of the percentage of nodes that had to lose edges in order to cut the graph in half over time. So at the bottom of the graph, we see all the dates that we collected data for. We cut them all in half, and here are the percentages of the number of nodes that we would have to essentially take down or affect in some way in order to majorly disrupt the malware distribution network. As you can see, these percentages range from around 5% down to about a half a percentage. So what we concluded is that the graph structure is relatively loosely coupled, not very robust, and relatively easy to disrupt. What a potential use for this is that we could, if we received an early indicator, such as what I have in the graph that I showed you earlier, some sort of buildup, and we identified a subsection of the malware distribution network that was infecting the rest of the nodes with something particularly interesting, then it would be relatively easy to segment that part of the distribution network off and stop the spread of whatever malware is being spread by those nodes. So next I'm going to talk to you about the methodology and how we collected this data. First, we started with from Alexa.com, the top 5,000 most visited domains on the internet. And here's an example of Alexa.com. You see number 1 is Google.com, number 2 is Facebook.com. Not very surprising. So we could get a large surface of websites to look at that would lead to an infected site in the MDN. We then took each of those sites and submitted them to a Bing API. We actually found a valid use for Bing, where we could look at, for this example here, we're looking at CNN.com and seeing all the third-party links linking off of CNN.com. We then so we had a massive amount of links on the 5,000 most visited domains, and we submitted each of those to a Google Safe Browsing check to see if they're malicious or not. Once we got some positive hits from Google Safe Browsing and found some nodes within our MDN, we would do that spidering that I described earlier, where we would build the entire MDN. We did this whole process 3 times a day for a number of months using 1 Windows and 5 Linux systems. So let me show you some other findings that we had from looking at our data. We identified 3 node types: a malware intermediary, a malware host, and a root malware host. And I'll explain what each of these does in the upcoming slides. Malware intermediary is a domain that simply redirects traffic from one URL to another, forming a chain to where the actual malware binary is stored. So there's no malware actually stored on a domain that acts as a malware intermediary. A malware host is a domain that was infected by some other node in the graph, either a malware intermediary or a malware host. So these domains actually have malware binary stored somewhere on the hard drive of a server behind that domain. A root malware host is interesting because this is a domain that has malware on their hard drive somewhere, but the malware did not come from anywhere on the graph, and we suspect that this is because these systems may have been compromised or be under some control by the malware authors or other malicious actors. Overall, we conducted 607 data collections, around 42,000 average nodes, over 200,000 unique domains, 56,000 IP addresses, 253 top-level domains. So .com, .org, everybody's represented as far as what sites were infected by looking at this data. Our most connected nodes, meaning the most nodes with the most ins and outs, not surprised, VK.com was our number 1 with 1,300 edges. That's Russian Facebook. Bitly is a URL shortener that could be used to hide URLs, to redirect users towards malware. T.co is Twitter's malware shortener, or URL shortener, sorry. It's a short way to malware, that's for sure. Interestingly, we found .gov domains in our data collections. Outside the US, we found 392 .gov domains, 30 .gov domains from the United States, 152 from China, and we did find one .mil. I don't have it up on the slide, but we were very surprised to see that. So some conclusions. These MDNs serve as the back-end distribution network of malware and malicious cyber events. The graph can be very large, consisting mostly of root malicious hosts and malware intermediaries. Domains of all types are represented, including .gov. The structural robustness is minimal, so it's relatively easy to disrupt. And evidence suggests that we can derive early warning indicators of cyber events from this. Next, we'd want to do deeper analysis of the collected data, attempt the same analysis with different data sets, and provide early warning indicators to those who are interested. And we have tons of data on this, so please contact us if you're interested. And here's the contact information of the project team. And that concludes. Thank you.